Okay, great. So, welcome everybody to this is the first colloquium presentation for the spring 2021 semester here at Augusta University in Augusta, Georgia. We started doing these open to the public via online on Zoom and YouTube last semester, and it's gone pretty well. So I'm doing it again this semester. So check out the schedule. If there's any talks that you want to go to, let me know, and you're definitely invited to them. Today, our first speaker is Dr. Shinya Katsumata, who's at the National Institute of Informatics in Tokyo, Japan. And Shinya's done a lot of really cool work on categorical models and effect type systems, and has done a lot of work that I know that I've been appreciating and using in my own research, especially related to graded effect systems. I think Shinya was one of the first people to suggest graded monads in effect systems. And so he's done some really cool stuff, and I'm excited to have him here today to give us our first presentation. So thank you, Shinya, and I'll let you just take it from here.
Thank you very much, Hale. Thank you for a very nice introduction. So hi, I'm Shinya Katsumata from National Institute of Informatics. So today I'm going to talk about codensity games for bisimilarity. So this is a kind of another track of my research pursuing the so-called liftings of monads and functors and its connection with the theory of bisimulations. Okay, so bisimulation and the bisimilarity are one of the fundamental concepts in the study of transition systems, and there have been many work to understand these two concepts from many different angles. And there's one classic result of characterizing the concept of bisimilarity through a game. So let me focus on the classic case of Kripke frame. It's a function from the set of state Q to the power set of Q. So it's like a binary relation regarded as a transition system. Then there is a result saying that two states are bisimilar in a Kripke frame Q if and only if this pair is a so-called winning position in a game called interactive game. So I explain this in the next slide. And the motivation of this work is to extend this picture to various settings. So the one direction is to replace this Kripke frame to some other kinds of transition systems, such as Markov chains, which is a probabilistic version of Kripke frame, and other systems. Then we might also want to use other notions of simulation, bisimulations, like simulations and so on. And also we may want to replace the concept of binary relation, which is underneath this argument, with some other mathematical structures such as metrics. And the contribution of this research is to address these three directions of generalizations using fibered category theory, and we establish the following result. So we first introduce a notion of codensity bisimilarity, and then design a new game called codensity game, and establish their kind of equivalence, the characterization result. Okay, so then what is the interactive game? So let me quickly review it. So given the Kripke frame delta, then maybe you might have seen this definition. A binary relation is a bisimulation relation if for any related pair of states by S, if you make a transition on one side, you can also make a transition on this other side so that the resulting states land in the relation S, and this holds on both sides like this. And then bisimulation relations are closed under arbitrary union. Therefore, there is always a largest bisimulation relation called bisimilarity relation. And then the question is, how do we understand this bisimilarity relation? And for this purpose, there is a game called interactive game. I learned this from Colin Sterling's very good article about this area. So the game is played by two players, spoiler, duplicator. Spoiler takes positions in the set Q square, therefore these are the positions. Duplicator takes position in the product of 2-point set, left and right, and Q square. So this is positions for the duplicator. And then the game proceeds as follows. First, spoiler chooses one side of the state. For instance, for this case, let's say spoiler chooses left one, then makes a transition from S. And then spoiler puts duplicators to this position. So L is the flag, which one is chosen by the spoiler. And then duplicator chooses the remaining one and make a transition, and then create a new pair of states, S prime, T prime, which is the spoiler's new position. Of course, spoiler can do the other side, like making a transition on the right. And then the theorem says that these two states are in a D winning position. Oh, sorry, yes, I have to talk about the winning condition first of all. So in this game, when the interaction continues forever, or when spoiler fails to find this T prime, then duplicator wins. And the theorem says that this pair of states, which is actually a spoiler's position, is a D winning position, namely the position where duplicator can win from this game, from the game beginning with this guy, if and only if these two states are bisimilar. Okay, so, and we want to generalize this nice characterization to various settings, like changing Kripke frames to Markov chains, or replacing bisimulations with other notions of simulations, for instance, simulations or some weakening of bisimulations. And also we want to work with metrics rather than relations. Like bisimulation metric is a kind of metric that tells us how far these two states are from the bisimilarity, and or how to say how similar these two states are. Yes, and but when we want to try this generalization with the previous definition, maybe it might be only me, but it's not quite immediate, because the design of the game is really hard-coded with the logical definition of the bisimulation. And in some, for instance, this for all exist is like for all exist. Yes, and this is also very similar to the game theoretic notion in the logic called Ahrenfeucht-Fries game. And therefore, to achieve this generalization, what we do is to borrow the power of abstraction from the category theory, especially the five-word category theory. Okay, so to address these generalizations, what we do in this work is the following. So here I put the data, categorical data underneath the definition of the traditional definition of bisimulation for Kripke frames. This is the power set functor. Here, this is a category of end relations. It's convenient to put this category here because we talk about bisimulation relations, bisimulation relations. So therefore, we regard them as objects in this category. And then here, we put something called a lifting of the power set functor to here. And these three data are working behind the definition of bisimulation for Kripke frames. And what we do is to generalize these data to the following setting. So first, we replace power set functor to some end functor, and the Kripke frame to F-coalgebras. And then this part will be abstracted to this something called the C-lat wedge vibration. And this lifting, which defines the bisimulation in the case of Kripke frames, with something called codensity lifting, which I will talk later. And then with this abstract level of formulation, there is a game called Codensity game that characterizes the bisimulation specified by this lifting called Codensity lifting, Codensity bisimilarity. Okay, so that's the plan. So basically we go from left to right. But before doing this, let me show you the kind of quick look at the Codensity game without too much category theory. This slide and the next slide is all within the set theory. So it's a conceptual description of Codensity game. So the description is the following. So first, I define the concept of codensity bisimulation as follows. So we say that a binary relation is a codensity bisimulation if for any test chosen from some test set over Q, if it's a valid test for this binary relation, then S passes this test. And this test Q valid pass are currently abstractly given, but later we instantiate them with some categorical data. And that's where we connect this conceptual description and categorical definition. And also there is one technical condition saying that valid and pass must map joins to meet in the next slide. Okay. Then the codensity game is conceptually described as follows. So spoilers' positions are binary relations over Q. Like they are all both binary relations. Duplicator's position is a test over Q. And then spoiler's move is like from S, spoiler chooses a test such that S fails to pass. So the kind of what spoiler wants to say is like, hey, what I have is not a codensity bisimulation because it fails to pass this test T. Then duplicator responds to this by showing another binary relation such that T is not a valid test to S prime. So duplicator makes the following counter argument like, yeah, it's true, but look at this S prime. Then your test is not valid for this S prime. So it's a bit funny counter argument, but anyway, the story goes like this. And when the interaction goes forever, or when spoiler fails to find this T, then duplicator wins. And now, let me show you the technical conditions that I postponed. So now, okay, so valid and pass map joins of a set of relations if the join of relations in W is valid if and only if all relations in W are valid, and the same for pass. And when valid and pass are relations between relations and tests satisfying these properties, then already we can show this characterization result for bisimilarity. The first thing you notice is that given a set of binary relations over Q, then the following two things are equivalent. Namely, when the game begins with any element in W, then duplicator can win in such a game. And such W is so it is equivalent to have such W and a W such that the join of all relations in W is a codensity by simulation. And from this, we obtain this. This is a corollary of this theorem, saying that if a binary relation is a D winning position, that is, when the game begins with R, then duplicator can win, if and only if R is included by the codensity by similarity relation. So in that sense, it under approximates the bisimilarity. Okay, so and then what the plan is to instantiate this test valid and pass with the categorical data, and that categorical data is designed so that it matches with the theory of categorical bisimulations for coalgebras. And that is what I'm going to do from now. Okay, so this is the plan of the talk. So we are here. We've seen the definition of bisimulations for Kripke frames. And in the part one, first, we generalize the power set functor with a functor, arbitrary functor, and then bring arbitrary lifting of the functor so that we can talk about generalized bisimulations for the relational setting. And then we replace this guy with something called fibration. And in this situation, we can do quite a wide range of theory of bisimulations in many transition systems. But this is actually too big. And currently, as far as I know, there is no game capturing the bisimilarity for this general setting. So therefore, we instantiate this F bar with something called codensity lifting. So this codensity lifting has a parameter, and by changing it, you can cover several existing notions of bisimulations by codensity liftings. Therefore, it has a generality to cover some range of simulations. And then a good thing is that for this notion of bisimilarity, there is a codensity game. Therefore, and that matches with this bisimilarity. Okay, that's the plan. Okay. Okay, so first we begin with the basics of coalgebra. So, so we start with any category C and any functor F. Then F coalgebra is a pair of an object in C and a morphism from Q to FQ, that's delta. And this is pretty much like Kripke frame. So it was P here in Z, as I wrote here. But the good thing about coalgebra is by swapping F with something else, you also get a different notion of the transition system. So for instance, a Markov chain for the discrete case can be described by something called probability distribution functor. So, so it takes a set Q and then returns the set of probability distributions over Q. Yeah. And this becomes a functor. Okay, and then, okay, now, okay, so we have just generalized the transition systems. Then how do we generalize the notion of bisimilarity for these transition systems expressed as coalgebras? And for this, we do a bit of analysis. So recall that this is the definition of bisimulation for Kripke frames, you know, this one. And then what we do is to massage its definition a bit. And we actually express this as a postfix point of the composite of two operations. One is called relation lifting, and the other is called inverse image. So, okay, inverse image operation is defined like this. So delta star takes a binary relation and then collects all the pairs of states such that the image by delta lands in R. Okay, so it's a kind of analog of inverse image of some subset along some function, the binary relation version. So the next part is a kind of extraction of the central part of this definition of bisimulation. So we just remove this one, and then we kind of separate this delta from the definition of bisimulation. So what we get is something called relation lifting. So it takes a binary relation over state like Q, and then now returns a binary relation over the power of Q. Like U and V are subsets of Q, and they are related when for any U in large U, there exists a V in large V such that they are related by the given S, and they are vice versa. Okay, then you can easily see that this definition is exactly this inclusion, like S included by delta star P bar S. This is just an unfolding of the definition. Okay, but then now here some category theoretic analysis comes in. So P bar is not just a set theoretic operation, but it can be seen as a structure called relation lifting of this power set functor, which I'm going to explain in the next slide. So in general, when you have a functor f over set, its relation lifting is a functor over E-rel, which is defined here, making this commute. And note that this is not unique. It's just, this is just a relationship between these two structures. It's not like constructing f bar from f yet. Just a statement between these two functors. Okay, then what is E-rel? So E-rel is the category of end relations. Objects are set X with a binary relation on it, like this. And the morphism from XP to YQ is functions over this carrier of the binary relations, such that F maps related things to related things. So, okay. And then the previous P bar, I wrote it only for the binary relations over the set of states of the Kripke frame, but it can be seen in a more bigger context. This P bar is actually like this. Okay, so it's a relation lifting. And then we realize that actually when the Kripke frame is replaced by the coalgebra, F coalgebra, then we can simply take some lifting of F and then just put it as a P bar. So that's the basic idea for the generalization. So, yes, generalization. So, okay. So given a functor F and a relation lifting F bar of F, then an F bar bisimulation on delta, which is a coalgebra now, is a binary relation S such that S is subset of the delta star F bar S. So nothing very, surprising. We just step-by-step generalizing things, but already this kind of covers quite a wide range of transition systems over set. And for this notion of bisimulation, there is a Baltag's game which characterizes the bisimilarity. So now the game is played by yes and no. So yes position is a pair of states. No's position is a binary relation over states. And then yes chooses a binary relation such that the position st is included by this delta star f bar r. So that appears here. Yes. And then no picks one element in R and then makes it into the next state, next position for yes. And for this game, our interest is the winning for yes. So therefore, when no cannot make this choice, or when this continues forever, then yes wins. And this pair of states is a winning position for yes, if and only if these two states are bisimilar. Okay, so that's pretty good. But then now when we want to move to the more general setting where notion of relation is replaced with something else, such as metric or even topology or some other things, then it's pretty hard to do this. At least I cannot find a good way to do this. And that's the step we take. So now we are going to replace this one with really abstract setting like something called fibration. Okay, so recall that we have decomposed the definition of bisimulation by inverse image and this lifting. So in this part, our focus is on this inverse image operation. So it's, yes, this is the inverse image. And then now we look at the type of this inverse image operation. So, okay, so I put this EREL to set functor here. The upper part is EREL, lower part is set. And delta is a function from Q to FQ. And this R is actually chosen from this R is actually a binary relation over FQ. Therefore, this delta star takes such thing, namely the binary relation over R, regarded as an EREL object, into another EREL object, namely Q with delta star R, because this is a binary relation over Q. And then, of course, forgetful functor maps this pair to Q. But then we can also easily check that this delta itself is now a morphism from this object to this object. Then if you learn category theory a bit, then you notice that this looks something like pullback. Because starting from such thing, you get square. That's the kind of visual understanding of pullback. So, and the fibration is an abstraction of this kind of this operation. So, this is still informal explanation, but I think this is good enough to catch the intuition of fibration. So, a functor P from E to B is a fibration if you can take the inverse image, or say pullback, of an object in the upper category along a morphism in the lower category. Of course, to this upper object must be sent to the codomain of F like this. And the result of the pullback is another object in the upper category that is mapped to I by P, and also it comes with a leg like this. And then it also enjoys some pullback-like property, universal property, but we have to be careful because now, upper part and the lower part are separated, so we can't simply draw a diagram like naively. So, but that's a bit tricky part. But that's the fibration, the idea of fibration. So here are examples of fibrations. So the functor from E rel to set is a fibration, but also we can restrict end relations to the equivalence relation, and then there is a forgetful functor. That's also a fibration. And the inverse image of an equivalence relation is just the kind of, how to say, the inverse image of the relation, as I said before. Just we collect such pairs that are mapped to the relation in X by F. You can check that this is a equivalence relation. Next, here I put the category of extended pseudometric spaces. So extended means that the metric can take infinity, and the pseudo means that the same, a different point can have distance 0. Okay, and then how do we define this inverse image? So we compose D and F like this. So we first send 2 points by F and then measure by the distance defined over J. And the last example is the forgetful functor from the category of topological spaces to set. And if you have learned the set theory and the topology theory, then you might have learned the initial topology. So given a topology on J, the initial topology is the along F is the coarsest topology over I that makes F continuous. Okay, so yeah, that's the fibration. And then, okay, so the fibration itself offers the functionality for taking inverse images. But then for the theory of bisimulations and bisimilarity, actually, it's nice to assume one more property, which I call C-lat wedge fibration. And for this, let me introduce the notion of fiber category. So a fiber category over I is a subcategory of E that consists of objects mapped to I and morphisms mapped to identity over I. So I is an object here. Then fiber category are like, they are all mapped to like this. Okay. And what does it mean? So intuitively, this fiber category is the collection of all the possible structures you can put on I. And I will show the example of fiber categories here. Okay, so for this fibration from equivalence relations to set, it's the collection of equivalence relations on I. For this fibration, it's the collection of extended pseudometrics on I. For this fibration, it is a set of topologies, all possible topologies on I. And the C-lat wedge fibration are fibrations where each fiber category is a complete lattice. And this inverse image operation preserves meets. So yes, so remember that inverse image is like this, and then it's like this. This equality holds. Okay, and this already implies quite a lot of information. Informations on the categories E and B, and one of them is that this E, every C-lat wedge fibration is a faithful functor. Therefore, I introduced this convention, like the home set of E is always a kind of subset of the home set of B of this format. Okay. Okay, so this ends the definition of fibration, but the reformulation of simulations in fiber setting is pretty easy. So we redefine the notion of lifting along fibrillation as a functor on the top, which makes this square commute. And once such f, p, f bar are given, then we can again redefine the notion of f bar by simulations for f coalgebras in B as this inequality. It's the S is less than or equal to the delta star provided by fibrillation, and f bar provided by the lifting, and then yes, and of S. Okay. Okay, so now we have arrived here, and now we move to the codensity lifting part. So we actually specialize this guy to those obtained by something called codensity lifting. So codensity lifting itself is a concrete way to construct this guy from lifting from F, and that's the so yeah, that's the codensity lifting, and it takes a parameter. So it takes three things like omega, an object in B, tau, which is F algebra, and pi, which is an object in E. And then codensity lifting is given in this form, and it's a little bit, how to say, magical. And I do not directly explain this one, but rather give its universal property. So first of all, why it's called codensity lifting? This is because this codensity lifting is an inverse image of this round pi. So this is the codensity monad of pi with pi. And then this alpha tau naturally arises from this tau map. It's a kind of canonical map. And we pull back this right Kerr extension of pi with pi. So it's a codensity monad with alpha. And this yields codensity lifting. And of course, there needs a bit of technical condition and like existence of right Kerr extension, but here I assume it. Okay, so and this already shows the universal property because in pullback, inverse image has universal property, and this is a kind of one aspect of that. So, in fact, the codensity lifting is the largest lifting among the liftings of F that lifts tau to E. So this condition means that, so when you have a lifting of F, you get this object anyway. Oh, sorry, you get this object anyway. But then the question is whether tau can be restricted as a map from here to here is another problem. So therefore, in this collection, we focus only those liftings that lifts tau to the category E, like this. And then the codensity lifting is the largest one among such things. So for instance, this already says that if you want to lift an F algebra to the upper category, then this offers a method. Okay. But then I think what's interesting is this codensity lifting shows many aspects in many different settings. For instance, when we work with the fibrillation of end relations, like this, which we used for the bisimulation for Kepler frames, then the codensity lifting takes a function like this, and the binary relation over omega as a parameter, pi as a parameter, and then it sends a binary relation on Q to the binary relation on FQ, where R is defined like this. So it takes a bit of time to explain this, but the point of this expression is the kind of similarity with the formula I showed in the definition of codensity games. So in the codensity games, I talked about like test, valid path, these things. And already the codensity lifting in this setting has a similar flavor. So test, valid, OK are defined like this. So test Q is the home set from Q to omega. Valid QST is the statement that T actually belongs to the home set of ELL. And OK with C prime T is a statement like this. So the C and C prime are mapped to, will be related when they are sent by tau FT. Okay, so it's a bit technical, but let me further instantiate this with some concrete choice of functors and the parameter. So we now set F to be the power set functor, the algebra to be the main function like this, and the relation over 2 to be this inequality like this. Then what you can show is that actually the codensity lifting with this parameter satisfies this. So this equality, showing this equality needs a bit of calculation, and you really need to think about it. But anyway, at the end of the day, you get this one. So the codensity lifting takes a binary relation on Q, and then constructs a binary relation on the power of Q. And this one is like one side of the definition of the bisimulation. When you flip this, you get the other side. But when we put equality, we actually don't get the definition of bisimulation. We get something else. And that's the tricky part. And yes, but there's a bit of mysterious behavior on codensity lifting. But on the other hand, this demonstrates how you can get different liftings by just changing parameters. The next example, I put this more quantitative category like metrics. And for this case, I choose the distribution, probability distribution functor D. And now for the parameter, the algebra part, we take the expectation function. So expectation of this distribution is just we do this. And also for pi, which must be a pseudometric on this 0 infinity interval, is this Euclidean metric. And then after unfolding the definition, you notice that this codensity lifting computes the Kantorovich metric. So we supply an extended pseudometric over dq, and then the resulting metric is the Kantorovich metric over dq. So therefore, codensity lifting also kind of in the quantitative setting, it's related to this Kantorovich metric. And we can also supply more than one parameter to the codensity lifting. And in that case, we just take the intersection of them like this. And this kind of adds extra flexibility and expressivity in the lifting method, to the lifting method. For instance, in 1991 paper, Larsen and Skoll introduced the notion of bisimulation for probabilistic systems. And there, they kind of implicitly used the following lifting method along the fibration from category of equivalence relations to set. So it takes an equivalence relation over the set of states, and then constructs a new equivalence relation over the set of distributions over Q. And this equivalence relation equates two probability distributions if they yield the same mass for any S-closed sets. And what we can show is that actually this lifting can be expressed as a multiple parameter codensity lifting. namely the intersection of single parameter codensity liftings. And the choice is here. So I do not go into the detail, but the point is that yes, this can be seen as a codensity lifting. Now we have introduced the lifting. So okay, let's use it for defining the notion of bisimulations. So starting from F, coalgebra functor, P, the fibration, and then instead of giving the lifting itself, we just give the parameters for the codensity lifting. Then we get this codensity lifting itself. And then we say that given a coalgebra, then now instead of binary relations, we talk about objects in E, or more specifically, objects in the fiber over Q. I mean, yeah, this one. And S is a codensity bisimulation if S is below delta star of this lifting of S. Now, by unfolding this definition again, then we get this characterization of codensity bisimilarity, namely, S is a bisimulation if for any morphism from Q to omega, and this is like text. And then when T belongs to this home set in E, this is like valid. Then the composite, like this. So we first go by the coalgebra map, and the T is from Q to omega, therefore we have this FQ to F omega. And then tau is a map from F omega to omega, therefore we go this. And the whole composition anyway belongs to B itself, but we can also show that this actually belongs to the smaller home set, namely ES pi. And this part corresponds to path. And from this, we can design a codensity game. So a codensity game with this setting for this coalgebra is played by spoiler and the duplicator. So spoiler's position is an object in the fiber over Q. So it's a generalization of binary relations, or say metrics, while duplicator takes positions in test Q, but now test Q is actually this home set. Therefore, spoiler's positions are objects, duplicator's positions are morphisms, and they exchange these two structures with each other. Then spoiler chooses a morphism such that S fails to pass, while duplicator chooses an object in the fiber such that T is invalid with respect to S prime. And the valid and the pass are defined like this because of this, the previous slide. And now, the valid and the pass defined in the previous slide satisfies this condition of sending maps to sending joins to meets. Like recall that we are looking at the complete lattice fibration, so therefore you can compute this join in the fiber, and then F belongs to this join W to pi if and only if for any S in W, F actually belongs to this home set. And this is kind of the same statement I showed, long time ago. Like this W is a set of duplicator winning positions if and only if its join is a codensity bisimulation. And therefore, R is a winning position for the duplicator if and only if R is below the codensity bisimilarity. So that's the kind of story, main story. And then okay, so in the next slide, there is a possible kind of generalization of this. For instance, we may want to allow multiple parameters like this instead of a single parameter. And in that case, we just update the game so that the duplicator position takes this index like this, but the rest is the same. Another generalization is to allow restriction on the position of the spoiler. So now suppose that you have find a subset of this fiber such that every element can be expressed by joins in the elements of G. Then spoiler actually need not to kind of use the whole object space. Actually, spoiler can only play on inside the G, and that's sufficient. So that's a bit technical, but this is also possible kind of generalization. And okay, so that's the story about Codensity games. So then now, okay, so I have generalized the stories from very concrete situation to the quite abstract setting, and then we might wonder what is good for. And one potential use of our framework is the following. So suppose that you have designed transition system by choosing coalgebra functor. And moreover, you introduced your notion of bisimulation on that system, and you have identified the lifting expressing that notion of bisimulation. Then you may want to design a game that characterizes that bisimulation. And one way is to handcraft the game by looking into the definition of all these systems and then give the definition. But our framework offers a kind of alternative way. So instead of handcrafting the game, find the parameter for the codensity lifting that yields the lifting you have. So this is the lifting you have. And if you find a parameter such that they are equal, then the codensity game with this parameter immediately gives the game you want. That is the game that characterizes the bisimilarity. And for instance, already we can apply this scenario to this case. So we have identified Larsen and Scott's the lifting for the Larsen and Scott's bisimulation, but as a multiple parameter codensity lifting. Therefore, by supplying these parameter here, we get a game that characterizes the bisimilarity and probabilistic bisimilarity. So that's the kind of potential use of our framework. So, okay, the conclusion. So we gave a codensity game that characterizes codensity bisimilarity, and that's based on the technique called codensity lifting, which has some parameters so that it can be instantiated to cover various notion of simulations. And then also we have generalized the setting of bisimulation from set theoretic one to the more abstract setting using vibration. Okay, so that's my talk. Thank you very much for your attention. Thank you.
Thanks a lot, Shinya. That was great. I really enjoyed this talk. I especially liked how, I mean, the research is really cool, but also your presentation was great. I liked how you started with, the current definitions and then sort of like slowly built up into your more abstract setting, which is great for especially my students who are watching this. So really shows off the ability to do that, and then the use of category theory to make things more general and be able to relate things. And so I thought that was really helpful. Does anybody have any questions for Shinya?
I have a question.
Sure. Yeah, go ahead.
Hi, Shinya. Do you have any papers or work in progress that we can look at about this?
Okay. So this is this is based on the Lick's paper published in 19 and we are currently submitting a paper to this year Lick's about adequacy and expressivity problem that's the kind of problem we often study in the quad algebra community, and we kind of discuss this problem using these codensity bisimulations, because that's one direction. And I'm not sure if this is put in archive yet, but yeah.
So you're saying that there's a LIX 2019 paper, and then you're writing something that builds on that?
Yeah, that's correct. Yeah.
Okay, thank you.
Hey, I have a question.
Sorry, I'll put the link to the paper in the chat, to the 2019 LIX paper that Shinya was talking about. Sorry, Joshua, go ahead.
So I just wonder whether these games have anything to do with cofunctors, because at one time you said that one player was choosing objects and the other was choosing morphisms, and that sounds kind of like a cofunctor, where it's a cofunctor is a map between categories that's not a functor. The map on objects goes one way, and then the map on morphisms goes the other way.
Sorry, so there was a bit of disruption of the sound, but so I wonder if I could catch the whole sentence. But you mentioned a profunctor or cofunctor?
Cofunctor.
Cofunctor.
Yeah. So the map on objects goes one way, and the map on morphisms goes the other way.
Yeah, I've only heard of the notion of cofunctor, but I've never looked into it. So it would be, yeah, thank you for your suggestions. I'll definitely look at it, and okay, yeah.
Yeah, David Spivak did some work on that, because categories are comonoids in poly, and then the natural morphisms between them are not functors, they're cofunctors.
Okay, yeah. Okay, yeah, great. Yeah, thanks for the link with cofunctors. Yes, okay.
No problem.
Yeah, there's a question from Dominic, actually, Dominic Orchard on YouTube. He asks, how does this relate to the GSOS approach of an abstract operational semantics, where we want to ask things about program equivalence, like algebraic?
Yeah, that's a good point. So it's, I think it's kind of orthogonal, but yes, we can certainly combine this. This, for instance, this codensity technique with this GSOS work. I think I have to say that I'm not very familiar with this GSOS work, but yeah, that's an interesting point. Especially, yeah. So this time I introduced kind of co-algebraic work, but yes, there's a bit of interaction between this co-algebra community and programming language community as well, like bringing notion of simulation by simulations to programs, or talk about them in a, so therefore, yeah, yes, that part is also kind of open area, I have to say.
Okay, great, cool. Yeah, thanks. Was there any other questions for Shinya? I had one question. It's something probably kind of simple, but earlier you were talking. You were talking about the fibrillation had to preserve meats, and I was wondering if which you then you needed it for the codensity lifting, I think. So is that an instantiation of a more general property about limits for those, or is it just about meats particularly?
Oh. So why maybe why meat only, or is that
Oh, yeah, well, that's my question. You had just mentioned it. Well, these preserve meets, and so I was wondering if that was if there was a more general property about all limits for those particular vibrations, or if it was just meets in particular.
Yeah, there's a bit of. I think there are several factors that made me to choose these vibrations. So, and for instance, we want to complete lattice because we want to express, simulations by simulations in this as a postfix point, and then we can apply the theory of clean fixed point.
Right. Yeah. Okay, that makes sense.
Yeah. And then, but then another choice would be like C-lat V vibration, like. But yeah, actually, every C-lat wedge vibration is a bivibration. Namely, this re-indexing, this delta star has a left adjoint. Therefore, it's also a C-lat V op vibration, and that's the kind of natural setting, I think. And many example also supports the choice of C-lat wedge vibration. Yeah. So.
Interesting.
Yeah. Good point, actually. Yeah. Thank you.
Yeah, it was a great talk. I learned a lot. All right. Well, if there's no more questions, we'll wrap it up. And thank you again, Shinya, for giving this talk, especially so late at night. In Japan, it's 11. Well, now it's midnight at this point. So we'll let you get off to bed.
And thank you very much for your attention. And yeah, thank you.
And thanks everyone for coming and viewing either on YouTube or Zoom. And if you have any questions about the colloquium in the future, let me know, and keep your eyes open on all the channels, and I'll be advertising more talks. So thanks a lot.
Thank you. Okay, thank you. Bye.
Yep. See you later.
See you.